This lesson is for FST, lesson 10.6 on binomial probability distributions. Keep in mind that this lesson is actually a combination of our two most recent lessons that we looked at. In 10.5, we did binomial probabilities, and in 10.4, we did probability distributions. Distributions is when you make a table of the probabilities and then graph them. Binomial probabilities is when you use our formula from yesterday, the n choose k, where k is the number of successes, n is the number of trials. Probability of success raised to the k times q, which is the complement of p to the n minus k power. That formula gives the probability of getting exactly k successes in n number of trials in a binomial situation or binomial experiment, in which the probability of success on each trial is calculated to be p. So we learned that formula in lesson 10.5. Now we're going to talk about how to graph it. So we're just going to jump right into an example. It's example 1 from our textbook. Assume a basketball player makes 75% of free throw attempts and that the attempts are independent of each other. Determine and graph the probability distribution for the number of free throws made in 8 attempts. First thing you should do is write out the formula. So we can reference this here to write it out. You need to give it a name. I'm going to call it B of k for basketball. K is going to be my variable now. If you wanted to call it x instead of k, that's fine, but know that our number of successes is the variable here, so I'm going to leave it as k. So I'm going to have 8 attempts, so that's my number of trials. K is going to stay as my variable. Probability of success was told to me this time as being 75%. That gets raised to the k. The complement of 75% is 25%. Then I raise it to the n minus k, or excuse me, to the 8 minus k power. So now I need to think about what the k values could potentially be. If you are shooting 8 baskets all together, is it possible that you only make none? None of the baskets go in. So keep in mind when you set up your table, k is your outcome, or your independent variable, and b of k, or the probability of k, is the dependent variable, or the outcome. So it is possible in your 8 attempts that you end up with anywhere from 0 all the way up to 8 total baskets. So there ends up being 9 outcomes if you include the fact that there's also a 0. Now to calculate each of the outcomes, we would need to tell the calculator to do 8 choose 0 for the first one. Then we would calculate again, 8 choose 1, 8 choose 2, 8 choose 3, and so on. So let's review how to do that on the calculator. You would choose the binomial, and would we use PDF or CDF here? Remember, we would use PDF. The CDF would add them all together for us. So even though we have a bunch that we have to do, we don't want them added, we want them individually. So we would do the PDF command. Keep in mind that it asks you for the n first, and the p next, and then the next value is optional. If you leave that one blank, it'll give you all 8 of them, or excuse me, all 9 of them, and it'll give them to you in one big long strip horizontally. And you would just use your right and left arrows on your Inspire to identify all of those values. I prefer not to do it that way. It's harder for me to track visually on a horizontal list. I like to do them each individually, and then I just highlight and copy and paste. So I'm going to do the problem multiple times, starting with 0, and I'm going to get an answer. Then I'm going to do it again. I'm going to type in a 1, do it again, type in a 2, and so on. I like having the answers given to me separately. But if you leave that number blank, you'll get all the answers in a list. So I've gone ahead and I've calculated all of those, and I've put them all in my table. Clearly we can see that the highest number of attempts is going to be 6, because 6 out of 8 is 75%. So that would be the highest percentage that we would expect to get. Now you're going to go ahead and graph all of those. Keep in mind that when you're typing in the table, I don't really care what you round to, but it would be preferable if you didn't round at all. I know I did do a little bit of rounding here just for time's sake, but typically you just type in what you're given, and then we're just going to graph these. Make sure you give yourself enough space. It's going to be quadrant 1 because none of these are negative. Give yourself enough room on the x-axis or the k-axis to do from 0 to 8. And then make sure on the y-axis that you come up with a scale that's appropriate. You don't want to give too small of a scale because then your graph won't be very dynamic looking. And you don't want to use too big of a scale because you don't really have a whole lot of room. Our biggest percentage is 0.31, so I want to pick a scale that's going to include numbers above that. So I'm going to do 0.1, 0.2, and so on. And then because I'm labeling every other, I've given myself plenty of room here. On the k-axis, I'm going to label every other as well, mostly just for time's sake. Please make sure that you label which axes is which, and please make sure you give it a title before you finish. I understand the fact that some of these are going to be super difficult to graph, especially accurately, so I will allow a little bit of fudge room here. You're not going to have to do them exactly correctly. I'm going to do the first 3 here kind of all together. So I've already graphed the first 3. Nothing really very exciting going on there. Then for 3, I want to do 0.02, 0.08, 0.20, 0.31, so it's going to be my tallest one, back down to 0.26, and back down to 0.1. And then we just connect all those with some vertical bars because this is going to look an awful lot like a histogram. One final note here on the graph, don't forget to give it a title, so we're just going to say free throws here. One final note about the graph, when we're graphing here, clearly we've gone above the number 8. So when we're looking at these k values, let's say for the first one here, keep in mind that when we do histograms, remember that there's really an interval that we're using. So we're looking at the values between 0 and 1 for that first bar. 0 is included, but 1 isn't. 1 would be in the next bar, and so that's why the graph looks the way that it does. So that's why the bars extend beyond the numbers that we were working with. So I'd like you to try this next one on your own, and I'll reveal the answers shortly. Go ahead and pause the video. So you can see the answer here. I used B again for breakfast. You could have used any other letter that you wanted to describe the formula. This one's going to be a lot easier because you only have 4 trials this time. Probability of success is much lower than our first one that we did, so our graph looks the way we would expect it to, and that the numbers are more dominant on the lower part of the scale rather than it was on our previous one where all the numbers were kind of shifting over to where the 6 was. Another comment here that I forgot to mention earlier, some vocab that we did way back in chapter 1 as it relates to histograms, that this graph is skewed, and we need to review which direction. This one has some tails going off to the left, so it is skewed left. Anytime there's a tail, that will skew the numbers that direction. Even though it looks like it's kind of leaning to the right, the tail makes it skew to the left. So just a quick review on that. So we have our formula here. There's 5 outcomes because 0 is included. You would have typed in, most likely, binomial PDF, and you would have typed in 4 number of trials, 0.3 for probability, and then you would have either typed in 1, 0 through 4, or you could have left it blank, and it would have given you all 5 outcomes in a row. And then I did shade every other bar here just to make it a little bit more visually exciting, but know that shading is not necessarily part of your results. Make sure that the axes are labeled, make sure your scales are labeled very clearly, make sure there's a title. If we were talking about this as a test question, probably get a point or 2 for the table, probably 2-3 points for the graph, and probably 1 or 2 points for the formula. So quite a lot of points involved in distribution questions like this. There are 2 more questions I want to briefly discuss and have you think about and ponder. What happens to the probability of success as it changes or increases? Got a bunch of graphs here, and the graphs go this direction and then they loop back down here and go across again. All of them have the number of trials fixed at 8. The probability starts on the upper left as 5%, then it goes up to 25%, 33%, 67%, 75%, and 95%. So the question is, as we move from a probability that's low all the way up to high, what's happening to the graph? So you can see that when we start with a low probability, it's skewed to the right. Then it becomes more and more symmetrical in shape, or almost like a bell-shaped curve, and then it starts skewing to the left. So that's pretty much what we would expect to happen in the graph. Very similarly, what happens when the number of trials changes? Notice that here the probabilities of these are all at 50%, so they're all extremely symmetrical, that bell-shaped curve again. But as the number of trials increases from left to right, clearly the graph is getting more spread out, and the tops of the spikes are becoming lower and lower. One thing that I think is important to note here is that the area, if you were to draw a line kind of outlining what this graph looks like, the area under that curve for all three graphs is going to be the same, even though the shape is technically changing. Remember that in probability distributions, the area under the curve always should equal 1 or 100%. I did find a animation of the two topics that we just talked about as the number of trials changes and as the probability of success changes. They actually have the graphs with sliders, so you can actually see what's happening to the graph as you change those. So check out the link here. It's also posted for you on Moodle. It's a really nice visual of the graphs that we just looked at.